the slides with you guys. So we are going to resume what we have learned last week, and then we should continue, right?
Yeah. Doctor, the slide enough to cover the course?
What do you mean? The slides?
Enough to cover the course?
Enough to cover the course. Yes, I mean, you mean is it the notes that I give to you will
Yeah,
be
with
asked
video,
during
slide with
exams
video,
or what? And assignments? Yes,
Yeah.
definitely. Answer is yes, because as what I've told you before, this course is more or less on the theory part. So, I mean, of course, the chapter 1 and chapter 2, I will not like going to ask beyond that, because I think the most important thing is to let you understand how you can like calculate things, how you can derive things, and how you can explain things. So, but the types of question or the scenario of the question will always going to be almost the same as your assignments or like in the notes. So I believe it should be fine. Okay, even for the corrosion part later on, probably the formulas and everything will be the same, but the scenario, the types of question will slightly twist a bit just to make it more analytic for you guys, right? And right, I think last week we stopped till here. I think on the ionic strength, activity coefficient, and ionic strength. I think before that, do you have any problems so far on like the exercise and whatsoever? I think I saw the homework that you have sent. I'm yet to evaluate it, but I guess most of you did a great job. And if you cannot like follow whatever we have learned for the past 2 lectures, let me know, okay, so that we can clarify it as soon as possible. And I think yesterday when I was in office, Mahdi came to discuss with me, especially regarding on this, okay, on this question. Right. As you know, for Nernst equation, okay, you have a different variations. I mean, either from cell potential equals to in cell, okay, minus with RT over F ln, I mean, product over reactant. So you can also have log, okay, 0.0509 over N, okay. So what he actually discussed with me is that the variation of Nyquist plot basically give you a range of K values. So if you try to use like the other variations of Nernst equation, like for example log K, okay, with a standard formula, I mean the standard values over here, you will get not the exact value, but just slightly different, probably like around 7 to 8, but the power is still the same, power of 71. Okay, so this is actually clear to tell you that the values, okay, that we use, sometimes it can be varies, and that also will give a variation in terms of the values. So I hope you guys can catch that, and we also have gone through Debye Huckel, okay, especially on activity coefficient and ionic strength. Ionic strength, we have, I mean, know how to calculate it, okay, using this formula, okay. So today we are going to continue, okay, with one of the most important examples. So as what, I mean, I always share, if I'm telling you guys that the part is considered important, so just put this as a note that, okay, I should like really understand these things, because probably most of your like tests exam question or what will be related on this kind of example. Okay, right. So in this example, in order to determine the standard potential for silver chloride silver electrode of a cell of platinum, okay, with silver, okay, platinum with silver electrodes deep in hydrochloric acid, okay, the EMF of a cell at a certain M is actually concentration, molality, because it is measured as a mole over mass. Okay, in fact, when you look at the unit, it will be mole over kilograms. Okay, for HCl is measured and then the value are listed as follows. So the experiment have a certain objective. Okay, probably just to let you know. Okay, let me draw something here. Right. The setup will be something like this. You have a cell, okay, equipped with platinum. Okay, this is a voltmeter. And then you have another one. This is actually the silver electrode. Can you guys hear me? I hope that I'm not talking alone.
Yes, we hear you, Doctor.
Okay, all right. Because I just afraid that because I'm accessing you guys from home, so I hope the internet connection will be fine. Okay, right. So this is basically the setup. You have a different concentration of acid. Okay, so this one you have a change of HCl concentration. Okay, and then you have a platinum and then silver. Of course, this will be anode and this will be cathode. So hydrogen gas will be produced because you see over here that in the cell notation you have H2 produced. Okay, and this is actually the electrolyte. So of course, during the process, this will be oxidized, and when silver oxidized reacted with Cl minus, it will form silver chloride layer or probably a product on the surface of this electrode. So the experiment is basically when you change the concentration of acid, you measure the potential value. So it's like you have a set of concentration, different concentration, you pour into the cell, and then you measure what will be the potential. Okay, so the potential will be read from here. All right, so if you remember back what I've told you, that concentration plays an important role in terms of the potential value, because all these are actually depending on the activity. If you have a high concentration of acid, it means that you have more H plus, isn't it? Okay, so when you have like more H plus, then of course you have more activity that will actually increase the values and so ever. Okay, all right. So over here, they have listed a value. Okay, concentrations. Okay, plus with the potential value measured. You'll see that as the concentration decrease, okay, the value of potential will be increased. Okay? And this actually have a certain reason, because when it become dilute, you see that it contains more water. Water is very conducting. Then, of course, the values of potential will be increased as well, right? So the question is, using Debye-Huckel extended law, okay, calculate the cell potential, okay, values for silver chloride silver electrodes, given that the electrolyte is 1:1 in dilute aqueous solution, okay, and log gamma plus minus, this is actually a standard value, okay, and log gamma plus minus is equals to minus 0.509, okay, okay, molality power of half, and then plus with B. B is also a standard factors, right? So how you are going to do that? How to solve this kind of question? Because the question is basically to ask what will be the cell potential. This is actually the aim, okay? So first, what you need to do is to determine the Nernst representation. I mean, for the for the cell. So of course, when you see over here, this is actually the notation. So you can write it, okay? Because you know over here, if you allow me, okay, you can write the half equation. Okay, so Ag will become Ag plus electron, and then you also have like 2H plus 2 electrons, that will become H2. Okay, so more or less this is basically the overall the respective half equation for anodic and also cathodic, right? So you just write it, okay? Like for example, over here, I combine the anodic and the cathodic because you know the E cell, okay? Can be shown over here. This is actually for your anode and this is actually for your cathode. So you just actually substitute the value, okay? Then you will get a representation that is actually equals to E naught cell minus RT over F ln A activity of H plus multiplied with activity of Cl minus, okay? Right. So the activity of H plus and Cl minus is also equals to the ionic coefficient of gamma plus mx. So this is actually multiply, okay? So gamma plus m multiply with gamma minus m, then you will get gamma plus minus square m square, right? And when you substitute okay, into this representation, you assume that this is actually the second term. You put it here, then you will get E cell is actually equals to E naught cell minus RT of F ln gamma plus minus m square, right? Okay. So what you are going to do next is that you are going to substitute the values. Okay. So over here, okay, we just substitute it, and then you will see that, okay, this one is actually if I already expanded, which means I multiply, okay, I open this bracket, so it will be RT over F multiplied with ln gamma plus minus, and then another term will be RT over F ln gamma m. So the difference over here is that I change from ln into log, okay, and this actually have a certain reason, because the reason is that I would like to relate it with the Debye equation. So the Debye equation, I think it will be best if you use it in log representation, okay? So if you change it into log, then you know that you have to multiply with a factor, which in this case, you have to multiply with 2.303. Okay, so this is actually a mathematical reasoning, because ln is actually a log with a base of 0, which means if you want to convert into log, so you have to multiply with this factor. Okay, all right. So where does this 2 comes from? 2 is actually coming from here, because this is actually when I factorize it, okay, since it is like gamma plus minus square and m square. So when I factorize it, it will power of 2, right? So when you actually change it, this is all like mathematical representation as well. So I just like multiply it with 2 as well. Okay. So for those who wondering like where this 2 comes from, this is actually coming from the power. Okay. So using the Debye equation for log gamma plus minus, okay, then you'll see that I actually substitutes, okay, gamma plus minus, log gamma plus minus with a value over here. Okay, so you'll see that the representation now become E cell, okay, equals to E naught cell minus with 4.606. This is actually as a result of multiplying this value, okay, RT over F log M, still the same thing, okay, plus, okay, 2.344. So where does this come from? Actually, if you look carefully, this is actually coming from the representation. Oops, what happened? Okay, you guys still can, you guys still can see it? I hope yes.
Yes, yes.
Okay, so the standard Debye Huckel value is basically like from here. Then when you actually substitute, make it into a simpler version, you get log gamma plus minus is equal to this one. Okay, minus 0.509. So this actually where this comes from. You can try. To put this in a value. Okay. So, and then after that you can split it, because maybe I can do it together with you. So let us just copy this thing. Okay. Right. Copy. And then probably I will paste it somewhere here. Oops. Kind of small. Just okay, to show you, just to show you how you can get things. Right. Okay, so when you substitute the whole thing, this whole thing into here, okay? So what's going to happen is you have two sets of notation. You have in the form of B as well, Bm. M is actually the concentration. So due to that, okay, so you have to multiply. You can actually split it into two. So that is why, if I substitute over here, you have like what, minus 4.606, okay, RT over F, okay. Then you will actually multiply it with this value as well, minus 0.59. Okay, so when you multiply with that value, what happened is that it will produce values, 2.344. Minus 4.606 multiplied with minus 0.509, then you get a positive 2.3, okay, 44, okay, in m power of half, okay, and then another term will be minus 4.606 RT of F multiplied with Bm, another term. So I hope this part is kind of clear. Is it clear for you guys? Is it clear? Okay, how you get this?
Yes, Doctor.
Yes.
All right.
Yes, Doctor.
So after that, we can rearrange the values. Rearranging, and then remember that the values of a gas constant used here is R equals to 8.314 joule over mole over Kelvin, and the temperature is equals to 301. What's the temperature over here? Okay, is it mentioned? Is it mentioned? Right. So this one is basically assuming that the temperature is equals to like what? Almost at the room temperature. Like room temperature is equals to 225, and when you actually plus with 273, you will get like what, 298. But this one 301, meaning that the temperature is actually equals to 28. So 28 or 25 or 30, it depends. I think maybe in this case, the temperature mentioned should be 28, temperature equals to 28 degrees C. Degree C. Okay. So don't worry, actually the working condition in each question will be mentioned. I guess maybe here I missed out. But never mind. I think since the temperature is equal to 28, so when you plus it with 273, then you get 301 Kelvin. Faraday's constant is actually equals to 96,500 or 96,400 or what. Excuse me. Okay, right. So what's next is basically you have to substitute those value to here. Okay, R, T, F. Okay, and then you'll get a final notation as follows. You will have E cell plus with 0.1183 log M minus with 0.0602 M power of half equals to E naught minus with 0.1183 Bm. So all this value is actually calculated after you have substituted the standards, parameters value. Okay, so if you look closely, okay, this actually more or less, if you simplify it, not really simplify, but if you assume, okay, that this one will be like a linear equation, or y equals to mx plus c, okay, you can actually calculate m, okay, by actually assuming that that will be the concentration. So the plot of E cell plus with 0.1183 log M minus with 0.0602 M power of half versus M will give a straight line, okay, with a slope of E naught at M equals to 0, right? So finally, after you have this notation, you will, of course, make a plot. But before you make a plot, you need to calculate the value. So this is actually the Debye-Huckel representation, okay, for this experiment. So you will calculate those values. So how to calculate this value, okay? So basically, you just substitute the potential value, okay, right? So the potential value over here, okay, is being inserted, okay, plus with 0.1183 log M. M is actually the concentration, okay, and M power of half is also a concentration. And remember for this one, okay, the potential value, it must be in volt, not in millivolt. The values I think listed over here is in millivolts, but probably for the calculation you need to use volt. So that is why I think I've mentioned here that the potential value must be in volt. So if you have 341, so this one it actually equals to 0.3419 volt, and the rest will follows like that. So you will actually calculate and you will have another new value. This will be a new derivative values with regards to Debye-Huckel consideration. Okay, so once you have this value, so you can make a plot, right? So what kinds of plot that you will make is basically from the values that you have calculated, considering the Debye-Huckel. This is actually the y-axis, E plus with 0.1138 log M minus 0.0602 M power of half. Okay, so versus with concentration in molality, so you will make a plot. So you will have a negative linear plot, okay? And then from here, actually, you will calculate what will be the slope. Okay, basically, if you use like a software like Excel or Origin to make the plot, you will have all these values. I mean the equation, the linear equation, including the R square. Okay, So the most important thing is we need these values. Because it actually tells you this is actually the values of m when you assume that the intersection occurs at 0. Okay, so when the concentration is equal to 0, then you will get the potential values is actually equals to 2.3 sorry 0.223, right? So the plot of E plus with 0.1183 log m minus 0.0602 m power of half versus m is shown in figure above. Assume that at intercept m is equal to 0, then you will get this value. So the potential value of silver chloride is equals to 0.2223 volt. Okay, so is it okay to everyone? Any questions so far?
Doctor, in slide 32, please. 33, 32, 32. In the last using the Debye-Huckel equation, Doctor, the third multiplied by Bm from where?
This one multiplied with Bm.
From log. From you insert the log y, log gamma.
Yes, from this one. I think in the question it have mentioned that the given Debye-Huckel representation is this one. I think now I give you the simplified Debye-Huckel equation, okay, which actually equals to log gamma plus minus is equals to 0 minus 0.509 m power of half, okay, plus with Bm. Okay, so this is actually the equation, the Debye-Huckel representation. So as I told you, since you have like rearranged, okay, your reaction into a nurse representation considering the activity, and as I said, activity can be related with activity coefficient. This is actually the representation. Then you will substitute this value, because overall, if you use this one, you cannot like actually relate it with Debye-Huckel, because Debye-Huckel is always related with activity coefficient, which in this case gamma. So you have to convert activity into activity coefficient. So this is actually the things, which we have seen before. Okay, activity of plus ion, ionic positive ions, and the activity of negative charge ions, okay, will equal to the activity coefficient for positive ions multiplied with the concentration. So from here, actually, you will see that it will become as this. Then when I substitute into this part, okay, you will have like ln gamma plus minus m square, because I factorize it, okay, and then I expand it, and when I expand, I substitute log gamma plus minus into the Debye-Huckel equation as mentioned in the question. So after that, you will get this. I think this one, actually, I just make it simplified. Otherwise, maybe it's a bit long to write, but you can try later on by expanding and like substitutes the value, whether you get or not this equation. I believe that you should get this, even though it's just a slight difference. Okay, as I mentioned over here, how you get 2.3 for 4 is because like this one, actually when you multiply, you will get minus 4.606, and then you multiply it with minus 0.509, then you will get positive 2.344. And the others is actually because I expand it, because this is actually plus. So when you multiply, when you substitute together, it becomes slightly longer. Okay, so this standard factor will be again multiply with B. So negative 4.606 multiplied with Bm, then you get Bm. Okay, all right. So is it okay?
Doctor, why is activity for Cl? Why we not used for Ag?
Sorry. Again?
The there is 1, 2, 3, the 4 line. ECL equal ECL minus RT over F.
Yes, okay.
Then activity H multiplying the activity CL.
Okay.
So why we didn't use activity of AG? Why CL? Because anode is AG and the cathode is H2.
Yeah, Mary, you please look over here again, because this is actually I have combined. So you know that the cell potential is actually a combination between anode and cathode. Okay.
Yeah.
So I have wrote somewhere here. I mean, like, this is actually the anode I think reaction, and this is actually the cathode reaction. So after I have simplified, because Ag and AgCl is in the form of solid, so it will not be take into account. So that is why, I mean, after cancellation, you will see what's remaining is only H plus and Cl minus. So that is why, I mean, after I have combined the anodic and also the cathodic part, you have the final, representation will be like this.
Yeah, doctor, Ag as element is 0, but as
Yeah,
ion is not 0.
yeah. So that's actually what I mean. I mean, this is actually from your anodic reaction, right?
Yeah.
And this is actually from your cathodic reaction. Okay. So after I have like expand this into nurse, then you see that, okay, this one is actually the E cell, and then this is actually the activity. So it's supposed to be like ECl minus, um, and then maybe multiplied with Ag, maybe activity of Ag plus, okay, over Ag.
Yeah.
But Ag plus,
Yeah.
I will not account that. And Ag I will not count it because it's in solid, but Ag plus. So why I actually didn't count Ag plus over here? Because
Yeah.
the type of electrolyte used over here is HCl. So the common ions. So remember, this is actually the keywords, common ion. The common ion that influence the overall reaction is basically HCl. Okay, so yeah, I mean, we cannot like use Ag, okay, because the potential value will strongly dependent with the concentration of acid, which H plus and Cl minus. So that is why, I mean, over here, I didn't actually account Ag plus over here. So otherwise, then it's not going to be useful. It's not going to help you, because otherwise it will be negligible, okay, because the concentration will be very low as compared to concentration of H plus, which is more major, more dominant in the electrolyte. Then of course, at the end you will get this. Is it okay, Madi?
Yeah, it's okay.
Okay, all right. Any other question so far?
Doctor, there is another question. When you institute the log gamma, you put m half.
Yeah,
But
this one.
in real equation, we have only 0.509 plus p. So from where we get m?
No, this one is actually in m. 0.0, 0.509 m. This is actually the unit, the unit. So meaning that over here, you must actually account the concentration. Okay?
Okay.
If you don't put the m value, then actually you cannot find the gamma plus minus, because this is actually the thing. It's always, I mean, the activity coefficient is always related with concentration.
So
Okay.
I should put m concentration.
Yes. Okay. So after you have like derived this, I mean, representation, and you have like calculate the derivative value. Okay, so next you are going to plot. So I think for this kind of question, okay, this a very favorite question that normally asked during exam or test. So what you need to do is, first you need to derive, okay, the equation. Okay, so what kind of equation that I'm talking about is this one. Okay, after you have consider the anodic and cathodic, and then after that you simplify it, you substitute with Debye-Huckel representation, then you will get this. You substitute into the these values, you calculate, then you will get this. So after you have derived the equation, then next is actually to find the derivative value. So this is actually the derivative value. Remember, the cell potential over here, it must be in voltage. Over here, the question is actually given in millivolts. So you need to actually change it into volts. So as I said, like this one, it becomes 0.3419. This one will be 0.4182, and the rest. And third, you will plot a graph. Okay. So what kind of graph that you need to plot is basically the derived value versus concentration, N. Then you'll get this. Okay. So after you get this, what you need to do next, okay? You need to find the linear equation values, okay? Find linear equation, okay? So after you have find the linear equation values, then you actually assumes that the concentration is at 0. So when the concentration is at 0, so X equal to 0, so multiply with 0, then you get this part is 0, then the potential value will be always equals to the y-intercept. Okay, right? So finally, the E naught value will be equals to the y-intercept. All right. So I just want to give you some tips if you have experienced this kind of question in your exam or in your test. Normally, I provide graph paper. I mean, if you have like face-to-face like or physical exam, I will ask the student to plot the graph, because if you plot the graph, this actually will carry you some marks, because I just want to see what will be the trend. You should get a negative linear trend, okay, not somewhere else. You should get a linear, negative linear trend. And then sometimes probably some may calculate the slope manually, but I will encourage you to calculate the linear equation using calculator. Your scientific calculator actually have a function that it can calculate the linear equation. I'm pretty sure that some of you may know how to use it. So what values that you need, you can use this value as your y and this value as your x. Okay, and it will actually generate you the linear equation. So those who still have no idea how to calculate or how to get the linear equation from your scientific calculator, maybe you can learn from your friend who actually have the knowledge, okay, to use, I mean, to calculate the linear equation using calculators. Okay, so anyone knows how to calculate or how to get linear equation using calculator? Siapa tahu? Anyone knows? Liana, you know?
Yes, I know, Doctor.
Okay. You know how to do it.
Yep.
Okay. And how about others? I mean, like Mahdi, you know how to get linear equation from calculator?
No, I don't know.
Maybe you have to start learn. You actually you can get it also in YouTube. I mean, if you use like Casio scientific calculator, they, I mean, show you. I mean, like how you can enter the x value and y value, and it will actually give you the linear equation.
I know how to get by manual, but not by.
I see. I mean, by manual you can also. I mean, like you can calculate it by selecting y2, y1, yeah, and then the difference of x2, x1. You also can do it, but I think during exam, you will have a limited time probably. So
Yes.
if you know how to use the calculator, you just use it and just make a straight line draw. No need to be too accurate. I mean, because we just want to see the trend only. Okay. So these
Okay.
a few tips that I would like to share with you if happen that you will answer this kind of question. Okay. So as I said, the bottom line of this question is basically you have a setup, okay, and then you have a different concentration of acid, and you put platinum and silver as the electrodes, and you measure the potential value at different concentration of acid. So with this, people might ask, what will be the standard potential, okay, of silver chloride electrode? I mean, considering the Debye-Huckel as standard law. So, you know, if you use, I mean, if you have to calculate using Debye-Huckel as standard law, then you know that you have to relate it with activity coefficient. So, not to worry. Normally for this representation, log gamma plus minus 0.509 m power of half plus bm is normally given. Okay, so you just need to do the maths to get the values and etc. Okay. Any other questions so far? Other that?
Doctor, can I
Yeah.
ask last question?
Yes.
Doctor, in slide 32 also. When we convert the activity from y gamma plus m multiplied by gamma minus m, from where insert 2 multiplied 2.303 log m minus 2 multiplied by 2.303 RT over F log gamma plus minus.
You mean like this one?
Yeah, here.
Okay.
From where we insert 2 multiplied 2.30.
Okay. I forgot your name again. What is your name?
Jihad.
Jihad. Okay. Oh, nice.
Yeah.
A very good name. Okay. So Jihad,
Thanks.
this is actually a mathematical constant value because you can see over here. Initially, I use ln. Ln is actually a log with a base of 0. Okay. And after that, I change it into log. The reason why I change it into log is because I try to relate it with my Debye-Huckel equation, because in my Debye-Huckel, actually I use log gamma plus minus. So I have to change, or I have to like use the Nernst equation in terms of log value. So the conversion from from ln to log, you need to multiply with a factor. This is actually the factor 2.303. Okay, and where does this 2 comes from? Actually, I told you earlier that this actually coming from the factorized square value. So you will get gamma plus minus square and then m square. So I just factorize it. You have square over here. So when you actually expanding or maybe you expand this part, then the 2 value will be multiplied in front. And 2.303 is actually the factor value from ln into log. Okay, Chad?
Okay, thanks, Doctor. Thanks.
All right. Okay. So I think further on, probably we will have a practice in your assignments. I will give a few questions related on these things. Right. So we are going to look at the other questions related on activity. So example 6, given that the EMF for example 5, okay, is equals to 0.3524 volt at 25 degrees C, when the concentration of HCl is equals to 0.1 molality. What is A, the activity of HCl, B, the average activity coefficient of HCl at this concentration, and C, the pH of the acid. Okay, so first, okay, looking at equation 1, after we have considered anodic and cathodic reaction, half equation, you will get this as a simplified form. So as I said again, why actually we use, didn't include Ag plus over here is because the activity, okay, or the potential is actually dependent on the activity of the acid, which in this case H plus and Cl minus. Okay, and that is why I think the Ag plus is not included over here because the concentration is negligible or very low. Okay, so you will get this representation. Okay, ln AH plus multiplied with ACl minus. Okay, so if you just, I mean, remove the ions, I mean, like consider that, okay, this is 1 to 1, then it will be activity plus minus square. Okay, so Y become like A plus minus because both are actually like 1 electrons, this one plus 1 and this minus 1, then I just like make it into activity plus minus square. Okay, so square because we multiply these two. Right, so if E cell is equals to 0.3524, because the question actually given the electromotive force, this is actually the term. I hope maybe you know what does it mean by EMF. In Malay, it calls diagerak electron. In English, it calls motion or electromotive force. Right. So when you substitute over here, okay, you will get ln A is actually equals to F over RT multiplied with 0.223 minus with 0.2524. Okay, so where does this come from? This is actually coming from, okay, the E naught cell value, because earlier on we calculate the E naught cell value. Okay, we get the E naught cell values from this calculation. So the E naught cell minus with E cell, then you'll get a values, okay, a negative value, and then you multiply with this value, and then you antilon the values, you get a positive 6.357 power of 10 minus 3. Okay, so A, okay, the activity either for H plus or either for Cl minus, because both actually the same. Okay, so you just square root the values, you will get 0.0796. Okay, so this is actually the concentration or the activity of HCl. All right. So next, the question B, the average activity coefficient. So since you know that A or activity plus minus is equals to gamma plus minus M, so gamma plus minus will be equal as this. So here you will get, okay, this one is a simple calculation, I mean, but I didn't show it. So A plus minus equals to gamma plus minus M. So earlier on you get A plus minus is equals to 0.0796. Okay, M is equals to 0.1. So I just like substitute here. Gamma plus minus is equals to A plus minus over M. Then you will get 0.0796 divided with 0.1. Then, of course, this one will result you 0.796. Okay? Is it okay?
Yes,
okay.
thank you, Doctor.
Right. And how about a pH? Because the question actually asked for pH. Okay. Forgot to tell you that pH is actually equals to negative log H plus or negative log activity of H plus. Okay, so always remember how you can calculate pH is actually from this notation. pH is always equals to negative log H plus. Okay, so since the concentration of H plus is already known, okay, so you just substitute negative log, okay, 0.0796, then you get 1.1, okay, pH, the value. Okay, so simple. You can try it again home. Right? So any other question so far before I move on?
No, it's clear, Doctor.
This one is okay, yeah? Mary, is it okay for you?
Yeah, okay.
Okay, all right. So we are moving on to the last part of chapter 1, probably to understand about a current flow. This not really related with potential and whatsoever, activity or what. Okay, so there are two types of current flow, okay, in electrochemical reaction. So first is known as Faraday, and the other one is known as non-Faraday. So you will hear people saying that, oh, this cell or this circuit is Faraday, or this circuit is non-Faraday, and what's actually the difference? So Faraday current actually tells you that the charge transfer across the electrified interface will be as a result of electrochemical reaction, with the amount of electrochemical reaction caused by the flow of current is proportional to the amount of electricity passed. Okay, so in this case, okay, the current, okay, or the reaction is always related with the flow of current. This is actually the keywords: flow of current proportional to the amount of electricity passed, or the charge passed. Q is actually equals to charge, okay? Charge equals to NFN, okay? N is actually the number of electrons, number of electrons, okay? Okay, and of course, capital N is the number of electron, and this is actually the valency, okay? And F is actually the Faraday constant. And non-Faraday actually associated, okay, the charge is associated with the movement of electrolyte ions, okay? So this actually in the case of the process of electrochemical is as a result of the movement, okay? The orientation of ions. This actually because of if you have like a solvent dipoles, you have a positive and negative dipole, which at the same time will create a net of charge movement. So this will basically produce a non-Faraday current. It's not the same as Faraday current. So Faraday current is more, I think, objective. You have like how much amount of current flowing is actually as a result of how much charge is being passed through. Okay. Meanwhile, for non-Faraday is always related with other effect, which is related to the movement of electrolyte ions. Not only on the reorientation of dipoles, it could be other things like adsorption or desorption, and also electrode to electrolyte interface. Because for adsorption and desorption, this is always related with like a gradient, a gradient, I think concentration gradient. Imagine that if you have like metals, and this is actually your electrolyte. So you have this interface, electrode to electrolyte interface. So when metals is being put in the electrolyte, it will oxidize and forming the positive charge, okay, on the surface of the metal. So when it forms a positive charge in the on the surface, what happens is actually it attracts, okay, negative charge ion, negative charge ion to go or to diffuse to the surface, okay, and this actually will create so-called electrostatic interaction. Okay, so this electrostatic is known as the first double layer form, Helmholtz double layer. Okay, so why, the negative charge is attracted? Because over here you will see that the concentration or the amount of positive charge ion is more. So of course it will attract the opposite side of charge to goes to it, to attract it to it. Okay, so maybe if you go to a function, you'll see there's a lot of ladies, then it will actually attract the guys to go, because you think, oh, okay, this is where you can find your couples or whatsoever. So the logic is like that. If you have like more concentrations of either positive charge ion or negative charge ion, then it will attract the opposite charge to attract to it. Okay, so this actually will be related to the non-Faraday current. So is it clear? Is it okay to everyone?
Yes, doctor.
Right. So the other part probably just for your information, because all these are actually more, I think, details. I mean, the details of like double layer and also like, for example, this one, the double layer and interface. You will learn it in chapter 3. Okay, in chapter 3. But never mind, I think it's just an introduction for you guys. What does it mean by ideal polarized electrode? Okay, so this one actually tells you that there's no charge transfer across the interface. The ion, okay, move in and out of the interfacial region in response to the potential changes. The interface behave as a capacitor and will be used as the storage device. So this one actually tells you if you have electrodes, okay, that have a properties of giving a polarized properties. It can actually have positive terminal and negative terminal at one end to the other end. The most, I think, related example would be capacitor, because capacitor, if you note over here, this is actually the symbol. Capacitor actually have like one positive and one negative terminality. So this actually tells you that when it established as it is, so there, I mean, without any connection to other things, there will be no charge transfer, okay, across it. So it will remain as it is. But if it is connected to something else, then what happened is it will give a response. I mean, it will give a polarized response. All right. So this more or less what I think I have explained to you briefly about just now. You have a metal dipped in electrolyte. So what will happen is the electrode will be oxidized, forming a positive charge, and it will attract the negatively charged ions. So the absorption will occur on the surface at the inner Helmholtz plane, IHP. You will heard this all over again, IHP, inner Helmholtz plane. Okay, because when you have negatively charged ion, I think attracted on the plane, okay, attracted on the surface, it will create like a plane, like one flat plane, okay, and then when you have like negatively charged ions over here, then it will attract another species, which like polyatoms, positively charged polyatom, to be attracted, okay, at the outer Helmholtz plane. This one OHP, outer Helmholtz plane. Okay, all right. And of course, the interaction is later on not via electrostatic. Electrostatic interaction occurs over here. Okay. Over here, I think now the interaction occurs after that will be on diffusion. Diffuse. Okay, diffusion. Right. So that's why you have like a compact layer and also a diffuse layer. Compact layer, it means that the inner Helmholtz and outer Helmholtz plane are from electrostatic forces and very strong. Diffuse layer is a gradient change of charge accumulation due to the thermal agitation. Okay. And then you also have like this one, the overall interface. Sigma is actually known as the interface. So the interface of a metal is basically the sum of the interface at the inner Helmholtz plane, including the interface at the outer Helmholtz plane and the diffuse interface. Right. So need not to worry. I think the last few slides, I'm not going to ask you more details about this in tests or whatsoever. This is just for your information only. Okay. Right. So I think this one probably I will skip because it's more or less related to point zero charge. It's off the topic, but I think the last two slides that probably I will discuss is factors that affecting electrochemical reaction. So electrochemical experiments and variables in electrochemical cell, you have different variables that can affect your reading. This is actually quite important. Probably you need to uh, take note on this. Okay, so you have like a first variable is actually related with the electrode variables. Okay, so if you have different size of electrodes, it will actually give you a different current value, a different, potential will always be the same, different current value and probably different times and etc. Because the area over here is actually different. So of course, the other things will be on the material, which type of metals that you use. Either it is a reactive metals, like for example, aluminium. You can also like use less noble, less reactive metals like copper or whatsoever. And you can see that if you use aluminium, okay, in the case of in your electrochemical series cells, you will see that the reaction will go faster because aluminium can easily oxidize. So of course, materials will be important, surface area, geometry, okay, and surface condition. Surface condition will always related with the the homogeneity of the surface. So that is why it is important before you start your electrochemical reaction to polish. Okay, to polish your electrode so that they will be outside layer removed, and it will give a more accurate measurements during your testing. Other than that, it will always related with mass transfer variable due to the modes of mass transfer, diffusion, convection, and others. Okay, I think mass transfer we will go through after this, the last part. Okay, the surface concentration and also adsorption. This will be what is related with mass transfer. You will also have a solution variables which actually related with the concentration of your electrolyte, okay, pH, type of solvent used, and etc. Fourth will be the external variables. Okay, the external will always going to be a physical variable. Of course, related with temperature, pressure, time, stirring, and whatsoever. Okay, and lastly, the other variables will be related with electrical variables. What will be the potential values used, current values used, and then quantity of electricity used. So all these are actually important to be considered when you do electrochemical experiment. Right. So allow me to talk a little bit on mass transfer. I guess this actually quite important for you guys to remember. So as you know, when you have electrode to electrolyte interaction, okay, this is where all the redox process occur. You have like oxidation process occur at your electrodes, and then after that, ions will be attracted. So that attraction or the process will known as adsorption. So the ions will be absorbed on the surface. So remember the difference between adsorption and absorption. Okay, so AD, adsorption means that the process is actually occurs on the surface only. Okay, on the surface, not penetrating to the material itself like sponge or whatsoever. So adsorption occurs here, and this is where the electron transfers occur, because during the oxidation process, okay, during the oxidation process, you will see that metals will be converted into metal plus electron. So this is where the electron is produced. Then it will be transferred into the ions that is attracted. Of course, the ions that will be attracted over here is negatively charged ion. Okay, the negatively charged ion will receive the electrons. Okay, and then the desorption process occurs where the outside product will be formed or whatsoever. So of course, you have a region known as charge transfer, and you also have a region known as mass transfer. Mass transfer is where your I think oxidant, probably the ions, the bulky ions will be diffused, okay, to go to the RHP or OHP region, okay. So mass transfer of a reactant to product and to and away from the electron interface. Electron transfer at the interface will occur, and then the proceeding of follow-up chemical reaction will occur, okay. And finally, the surface processes, which is the adsorption or desorption, will occur. So, of course, the interaction, the electrostatic interaction that occurs here is known as adsorption. And then after it receives the electron, what happens is it will become stable. And then this is where the desorption process occurs. Right? If you have like here silver, silver, and then silver will be converted into silver plus. Of course, if you use like HCl, then the Cl minus will be attracted here. Then when the electron transfer occurs, this will actually form EgCl. Okay, this is where the desorption process occurs. It forms a stable product. Then right. So mass transports can occur via three important methods. This also important for you guys to remember. Okay, for mass transport, you have first is known as migration. Second, diffusion. And finally, convection. Okay. So the process that occurs first is known as migration. So migration is something like this. So you have working electrodes or metals deep in your electrolyte. So when it oxidizes, as I said, it will form positively charged ion. Okay. Then this will attract negatively charged ion onto the surface. Okay. So this IHP, inner Helmholtz plane, the process, of course, is known as electrostatic interaction. So the modes, how this negatively charged ion will be, can be attracted to the positively charged ion is known as migration. Okay, migration will always related with the movement of the charged body under the influence of electric field. In this case, because of you have positively charged ion, then migration will occur. So people will migrate. Ions will migrate from the outer Helmholtz region. This is actually the outer Helmholtz region, outer Helmholtz plane, okay, to the inner Helmholtz plane. So this process is known as migration. Okay, so next, after the adsorbed negatively charged ion forms on the surface, this actually will create another effect known as diffusion, because after the surface has been covered with negatively charged ion, it will actually attract not electrostatically, but due to diffusion. Okay, you will see that if you have a polyatom, okay, so this one is positively charged, it will be get closer into negatively charged plane. So this process is known as diffusion. Okay, diffusion happens actually occurs because of it actually as the influence of concentration gradient. Over here, you will see that since negatively charged ion have been like absorbed on the surface, the concentration of negatively charged ion at inner Helmholtz plane will be higher as compared to the concentration of negatively charged ion at the outer Helmholtz plane. Then this will create diffusion. Okay. And finally, the modes of mass transport can also occur via convection. Convection is more or less like a physical effect. Okay, so this is actually more or less like a physical effect where it is always related with mechanical stirring, aeration, and whatsoever. Stirring, aeration, bubbling, etc. Okay, because when you stir, okay, you are mechanically mobilize the solution or the electrons, sorry, the ions inside it, and this actually creating an effect, the so-called as convection. Okay, all right. So all these three modes of mass transport need to be memorized because later on in chapter 3 you will learn about double layer and you will apply the knowledge on mass transport to explain different models of double layer. Okay, any question so far? Anything you want to ask? Shamira, okay?
Okay, good.
Okay, good. Okay, never mind. Don't worry. I have already recorded this, so you can hear it all over again. I mean, like, yeah. But I think maybe because of now you still cannot see probably on double layer. But as I can tell you, when you put the electrodes inside the electrolyte, this actually will create an interface. You have an interface between working electrode or electrode to the electrolyte. So as you know, working electrode or your metals will be oxidized when you put in the electrolyte. So when it oxidizes, it forms a positively charged, and at the same time, how the electrochemical process proceeds, this is actually due to the interaction of ions. So start, I mean, from the transfer of electrons because of like diffusion, I mean, absorptions, and then after that, another effect will be on diffusion and whatsoever. Okay, all right. So I guess that's it for chapter 1. Okay, right. Yes. Save this one first. Okay. And remember today, I think after the class, I will actually post a quiz question. So it's an online quiz. I will post in your e-learning. So you will be given a time until like 5 p.m. to do the quiz, and then you can submit it back to the e-learning. So what you can do is you can answer, I don't know, maybe on a piece of paper, or you can answer it directly from there, and then make it into PDF, submit it into the e-learning. Okay. So the question is more or less what we have learned so far on, like, I mean, self-notation, the definition, and whatsoever. Okay. So not going to be like too difficult. Okay. So no worries. I guess since it's just to like follow up with you guys, um, the the course and everything. All right. So we move to the next one. Probably just an introduction of chapter 2 before we call for the day. I guess maybe it's already like too much for you guys. I don't know. But hopefully you guys can follow it. Wait. Let me share the slides with you guys. Okay. You can see the slides?
No, I cannot see that.
Cannot.
Yeah, I cannot.
Now, still? Already? You can see the slides already? No,
No,
not yet?
no,
Yeah.
not yet.
No. Lena, tak ada eh? Lena, tak ada?
Yeah, yes. I didn't
Ada nampak
see.
slide?
Saya tak nampak slide apa-apa, Doktor.
Oh, ya ke?
Kena share balik kot, Doktor.
Macam mana sekarang? Okay.
Okay,
Saya nampak.
Okay, alright. Nazira senyap hari ni. Nazira ada ke? Tengah kerja kot.
Tak adalah, ada je.
Okay. And Mariam, are you around?
Ada je.
Okay. Alright. Probably for this one, I mean, chapter 2, I'm not going to like go to detail, like just like maybe have a chat with you guys. What's the input or what will be the aim for this chapter, right? For chapter 2, actually, we will go on thermodynamics and potential. So when I talk about thermodynamics, can someone tell me what is actually it's all about? I mean, what you can think of when I say thermodynamics?
There must be some heat involved.
Okay.
Delta G is delta S.
Delta G, delta S, yes, that will be the secondary. That's what you will get after that. But what is important? I mean, why thermodynamics is considered important? Hamda? Any opinion? What does it mean by thermodynamics?
Chemical reactions involving heat.
Sorry again, cannot hear you.
Reactions involving heat.
Okay. Well, thermodynamics is actually a study of effect of temperature. Okay. So meaning that if you study your experiment at different temperature, 30, 40, 50, 60, then this automatically is known as thermodynamics, because reaction will occur differently at different temperature. This is actually the norm, because the reaction always occurs because of you have like collision of atoms and then whatsoever. So when you have an effect of temperature actually will happen externally. And when you heat up, for example, your electrolyte, you heat up your electrolyte. So what things you can imagine? The atoms inside your electrolyte will be absorbing the energy from outside and then making it more vigorous, making it more like vibrate more, and then and the collision will occurs more. And at the end, you will observe that any temperature will give a faster process, because it will actually increase the acceleration or the collision of atoms between atoms, and then conversion between reactant into product will happen more faster. Okay, all right. And at the same time, when we talk about thermodynamics, you can also relate it with energy, the behavior of energy, because like thermodynamics is always related with enthalpy, okay, and free energy, activation energy, and entropy. Entropy is the arrangement of atoms. But yeah, I mean, if I ask you, okay, if you have delta G value, delta G is actually free Gibbs value. Delta G value that is equals to negative and positive. If it is negative, what you can tell about the process? Mahdi?
It is a spontaneous.
Yes, I mean, we are talking about spontaneity. When the free energy is negative, meaning that if you look into like energy diagram, I mean, of course, we show it here. Okay, energy diagram. So you have like from reactant to product. So this reactant, then product. Okay, so this till here is actually known as activation energy. The energy required to break, to achieve the optimum point where after that it will be resulting a different types of species. And then delta G is actually the overall values. Okay. So this is actually delta G. Okay. When you have a lower delta G value, which means negative or whatsoever, then it means that the conversion between reactant into product is easier because it doesn't require much energy to overcome, and then the conversion between reactant to product will occur spontaneous. So that is why, I mean, like we always talk like delta G equals to negative. This will relate to, I mean, spontaneous reaction. So all this actually have a reflect if you study it at a different temperature, because a different temperature will of course give you different behavior. Okay, so that is why sometimes people use thermodynamic values to calculate EA, activation energy, delta G, delta H, delta S using Van Hoff equation and whatsoever. Okay, so if I want to calculate activation energy using thermodynamic values, what kinds of equation that normally I use? I mean, this just to test your knowledge on thermodynamics. You've learned this before. I mean, like if I want to calculate activation energy, what formula that I should use? Mariam, do you have any idea?
So the delta G is it's equal minus negative nRT.
That one is for delta G. The question is if I want to calculate like activation energy, what kinds of formula that I will use? Anyone? Yeah. I mean, you learn about this. I mean, anyone knows? Just need the name only. Shamira, boleh agak-agak? Not sure?
Arrhenius equation.
Yes. Arrhenius, finally someone said it. Arrhenius equation. Okay. So Arrhenius equation is a very useful equation if you want to calculate activation energy with respect to different rate and different temperature. Okay, right. So in Arrhenius equation, you have like K rate of reaction equals to A exponent negative EA over RT. So if I make this into ln, so I change it to ln K equals to ln A minus EA over RT. And if, like for example, I make a plot, like ln K versus 1 over T, okay, you get like a slope or whatsoever. So this, linear equation can be related to, okay, ln K equals to ln A minus EAR, okay, 1T. Okay. All right. So the slope, okay, the slope will always going to be this one. Okay. The y-intercept will be here. Okay. This will be your y-intercept. Okay. All right. So it's kind of useful because when you have like a different temperature, then you will have different rate. Okay. And the rate is basically depends on the reaction, whether it follows like first order, second order, okay, or you are talking about different kinds of rate of reaction. Maybe like from nurse, you have like ln K from nurse or whatsoever. Then for each temperature, you will have different values, and at the end, you can calculate the activation energy, right? But sometimes activation energy can be used, okay, to relate the modes of the process, because imagine that EA, if the value is around 40 and below, kilojoule per mole, this will always related with physical absorption or physical absorption. Okay, and then if the value is larger than 80 kilojoule per mole, then this will always related with chemical absorption or chemi-absorption. Okay, all right. So as mentioned in the slides, thermodynamics encompasses system at equilibrium. So chemical reversibility is chemical reaction that is associated with the electrochemical reaction. Okay, and then thermodynamic reversibility. Okay, it's the infinitesimal driving force that causes the reaction to move forward or reverse direction, essentially at equilibrium. And the practical reversibility is actually the actual processes occurs at finite rates, therefore they cannot proceed at through equilibrium. However, processes can be carried out in a manner which thermodynamic consideration can be applied. So this is always the things that you see even before this, the next representation. Okay. All right. And then this is actually the few sets of formula related with thermodynamics quantity. Okay. Like delta G is equals to NFE. Okay. So remember this formula is known as Faraday's formula, Faraday's equation. Delta G is equal to NFE. Okay. E is actually the cell potential, F Faraday constant, and is the valency. You can also calculate delta S. Okay, delta S is the entropy that is actually equals to a change of delta G over change of temperature at the constant pressure. Okay, and then you can also calculate delta H using Van Hoff equation, which delta H is equal to delta G plus T delta S, temperature multiplied with the change of entropy. And finally, you can also relate the rate of reaction or the RT ln K, the rate of reaction equals to negative delta G, okay, which is also equals to NFE. Okay, all right. So I think the rest probably we will go through later on. I mean, not today. Right, and I think I forgot to tell you that this Thursday, I actually have a workshop in Sirin. I mean, on Kurosha. It's actually 2 days, starting from tomorrow until Thursday. And I believe probably we have to reschedule the class for Thursday only. Okay, so not sure if you guys are okay to have it maybe like tonight or maybe tomorrow night. Is it okay? I mean, just for 1 hour class only. I mean, in the evening, and then after that, I think we don't have class on Thursday. This Thursday only. But next week we are going to have as usual at this similar time. Is it okay? I don't know. You have anything to do like tonight or maybe tomorrow night?
For me, it's okay, Doctor.
Okay, so later on we will decide in the WhatsApp group if it's possible. Then probably we just have like only 1 hour class lecture online, and those who cannot join, maybe you can watch the recording later on. But so far for today, is there any question so far? Anything you want to ask?
No, it's clear.
That's great, Doctor.
Okay, all right. So, okay, again, thank you very much for your time. And then we will adjourn it here. I will post your quiz after this. And as I said, the limit given is until 5 p.m. And if you have any problems for your quiz, just let me know later on. Okay? So thank you very much, guys, for your kind attention.
Thank you so
And
much.
I wish you a very good day. So thank
Thanks,
you very much.
Doctor. Thanks,
Assalamualaikum,
Doctor.
and see you probably tonight or tomorrow. Okay? Bye.
Okay.
Okay, Doctor.
Thank you, Doctor.
Thank you so much,
Thank you,
Doctor.
Doctor.
Welcome.
Okay, my friends, everyone, hello, can you guys hear
Yeah.
me? I just want to tell you guys, you guys can check on the YouTube for the calculator to what? To calculate the equation in the calculator. And I will try to share the YouTube link, and then if you guys, but it actually difference in different calculator. If you guys
Okay.
have different YouTube link,
Different models, huh?
yes.
Okay.
If you guys have different, and then you guys can share it with all of us. Thank you.
So you will
Thank you,
share in
Leona.
the WhatsApp group, huh?
Yes, in the WhatsApp group.
Thank you very much, Lena. I appreciate
Thank you,
it.
Leona.
Okay, bye bye.
Okay. All right, guys. Thank you.
Okay, Doctor. Bye.
Okay. Goodbye.